young math padawans. It's Mrs. Angel with your lesson for today on quadratic transformations. So what in the world is a transformation? A transformation is a change in the form or appearance of something. So in this video, we're going to be exploring the changes in the form and appearance of quadratics. So as we recall, the parent function of a quadratic is y equals x squared. When we graph a quadratic, what happens with the solutions is they form a parabola because squaring produces the same output for two different inputs. So what we're doing here is we're taking this basic function and then we're applying three possible changes to it. One of the changes that we could apply is by multiplying our function by a number. Now, depending on the number that we choose, it's going to have a different result. For example, if the absolute value of that number is greater than 1, meaning the digit itself, whether positive or negative, is larger than 1, it's going to apply what's called a stretch. If we multiply it by a fraction or a decimal between 0 and 1, again, the digit is between, then it's going to apply what's called a shrink. And finally, if we multiply by a value that is less than 0, that's going to cause our parabola to reflect. The second transformation we're going to look at is what happens when we add something onto our parent function. Well, that causes our outputs to either increase or decrease, thus causing our graph to vertically shift up or down. And finally, the last transformation and the most important one we're going to look at is what happens when you actually change the base of your quadratic. And that's called a horizontal translation or a shift to the right or left. So we're going to be looking throughout these three transformations individually, and then at the end, we're going to look at how they appear when you combine them all in the same function. Grab your notes and let's get started. The first transformation we are going to explore is what's called a stretch, a shrink, and a reflection. And all of this has to do with what you're multiplying your quadratic by. In a stretch, we're multiplying by a number whose absolute value is greater than 1. In a shrink, that value is a fraction that is between 0 and 1. And in a reflection, that value is any negative number. So let's take a look at what all three of these look like together. So here we have a Desmos that's already set up for us to observe what happens when we change the value of A. So right now, the value of A is 1, meaning there is no change, and my new function is the exact same as my parent function. But what happens if I change that value? What happens as A increases, let's say to 4? Now my quadratic is much thinner than the parent function, and if we look in the table, that's because all of my outputs have now increased by a factor of 4, which means where my output used to just be 1, now my output is 4. And where my output used to just be 4, now my output is 16. So this is called a vertical stretch because your outputs are increasing faster than they were in the parent function. Now let's look at what happens when I move my slider and make A value less than 1, but also greater than 0. In other words, a fraction. You'll notice here that now our graph has become wider than the parent function. And in our table, because we're multiplying by a fraction of 1/2, all of our outputs are now half of the parent function outputs. This is called a vertical shrink because where I used to have an output of 1, now I only have an output of 1/2. Where I used to have an output of 4, now I only have an output of 2. All of my outputs have now been shrunk because my graph is growing at a slower rate. The final one is what happens when I multiply by a value less than 0, a negative number. And as you can see, if I just make this -1, all of my outputs have become negative because I'm taking my parent function and making them all negative. That causes your graph to reflect into the negative side of the x-axis. Now I could also then, from here, stretch it to a factor of, let's say, 5. So now not only is this a reflection, but it's also a stretch because I'm multiplying by 5, essentially, -5. Or I could do a shrink by multiplying by a value between 0 and 1, or in this case, 0 and -1. So again, the three transformations that we'll be exploring is the stretch, the shrink, and the reflection. So now that we've seen all three, let's take a closer look at each individual one. The first one is the stretch. So the table over here has the parent function values already inputted. Why don't you go ahead and apply the stretch of a factor of 2? In other words, fill in the rest of this table now. All you have to do is take each of your outputs and double them, multiply them by a factor of 2. So what's happening in the graph and the table? Well, our outputs are increasing twice as fast as the parent function, causing that parabola to vertically stretch. As something increases at a faster rate, it's going to grow much faster, and your parabola is going to get thinner and thinner and thinner. The next one we looked at was our vertical shrink. Why don't you go ahead and fill in the rest of the table for 1/2x? Great job. So to do this, all you had to do was multiply each of these values by half. What does this do to the graph? Well, now your outputs are increasing half as fast as your parent function, causing that parabola to vertically shrink. In other words, because I'm not growing as fast, it's like you're compressing on top of those values, and the parabola is going to get wider and wider. The final effect of multiplying is when you multiply by a value less than 0 or a negative value. So here we can see our new function is negative 1x. So go ahead and fill in the rest of these values now. So what happened? Well, we see a lot of the same outputs. The only difference is now they've all become negative, causing that parabola to reflect because now you've moved to the negative half of the coordinate plane. The second transformation we're going to talk about is called a vertical shift. There are 2 possible shifts that we're going to explore, our shift up and our shift down. So here I have a graph that is already ready to go. I have the form y equals x squared plus k, meaning we have our parent function, and then we're going to add a value onto it. So right now, the value of k is 0, which means I'm not adding anything onto it, and my new function looks identical to my parent function. But what happens if I add a positive value to it? As you can see in the graph, all of our points are shifting directly up that number of units. And in the table, you can see the same change. If I add 8 onto this graph, all of my outputs will increase by a value of 8. In the graph, everything is shifted up 8 units because now I have 8 more as the output than I originally did. What happens if I go the other direction? As I start to go into the negative values, you can see that my graph is starting to shift down. Each of my points is now directly below the points in the parent function, and in the graph, I've now subtracted 8 from each of my outputs. So as you add something on to your parent function, it's going to shift your graph up or down along the same vertical line. So let's practice doing one of these vertical shifts. Here we have a function y equals x squared plus 2. Again, I already have the parent in there. Why don't you go ahead and fill in the rest of this table now? Simple as adding 2 to each of your outputs. What does it look like in the graph? Well, now that all your outputs are 2 more than the parent function, your parabola is going to shift up 2 units. What about if it shifts in the other direction? So here we have a function of x squared minus 2. Go ahead and fill in this table now. Great job. It's as simple as subtracting 2 from each of your outputs. So what change does this apply? Well, all of our outputs are 2 less than the original outputs in the parent function. So now my graph has shifted down 2 units. The final transformation is the hardest one to master. This is called a horizontal shift, meaning that we're going to be shifting our graph either left or right. Let's go ahead and explore what this looks like. So right now we have a parent function, and what we're doing essentially with a horizontal shift is we're going to end up changing the base of this function. So since h is 0, that means it's matching up perfectly with my parent function because there is no change. What happens if I change h to a positive number? It'll start to shift to the right, and you'll really see the shift in that vertex. Our vertex started at 0, 0. Now it's at 4, 0. Now what happens when h is negative 4? Well, now my graph is starting to shift to the left. And that's because my vertex, which used to be at 0, 0, is now at negative 4, 0. The toughest part about horizontal translation is the fact that the formula has subtraction in it. So really, when I plug in negative 4, this would be the function y equals x plus 4 squared. And if I were to substitute in positive 4, that would be the function y equals x minus 4 squared. So how do we apply this horizontal shift in a graph? Well, as we saw in the slider example, what's happening here is a change in our inputs, not necessarily a change in our outputs. So the first thing we have to do is figure out what was the change in our vertex. Well, the vertex is unique. It's the only point in our parabola which has an output of 0. So we ask ourselves, what plus 2 equals 0? Because if I can make this base 0, I can find the vertex. Well, that would be a value of -2 because -2 plus 2 is 0. So what's really happening here? Well, our vertex is shifted 2 units to the left from 0, 0 to -2, 0. And what does that do? Well, it causes the rest of our points to also shift. So your inputs are going to change, but not necessarily your outputs. So what's happening when we shift to the right? We ask ourselves the same thing. What value -2 will equal 0? Because I want to find the vertex, and the vertex will lead me to my set of endpoints. That would be 2 minus 2 is 0. So I can now see that my vertex has shifted to the right 2 units, causing every other point in my table to also shift to the right. So now my inputs have to change to produce the same series of outputs as my parent function. So now that we've had a chance to observe all 3 transformations individually, let's take a look at what we would do if we were given a combination of them. So there's 3 steps here. The first step is you want to take a look at where your inputs are going to be. So that shift on the vertex is going to affect the rest of the work you do. From there, we're then going to apply whatever the value of A is. That means it could either stretch, shrink, and or reflect our graph. Finally, once we've done that, we'll find our outputs by applying any vertical shift that we see. So here's our first example. So we can already predict what these transformations are going to be. Because we see a factor out in front, we know that this is going to be stretched by a factor of 2. We also know that because the base of the function has become a difference, that this is going to end up shifting right 2 units, and we know that this parabola will be shifted up 2 units. So to start off graphing this function, we're just going to look at what's inside of the parentheses. And that right now is the function x minus 2 quantity squared. So we're just going to start there because that's going to show us what inputs we can actually use here. So the first input that we want to find is our vertex. We are trying to find that unique point that makes the base of the power 0. So looking here, what value of x would we have to plug in to make the entire base equal to 0? 2 minus 2 is 0, and 0 squared is 0. So here, it looks like our vertex is going to shift over to positive 2. Now, that's not where our vertex is going to end because we still have other transformations to do. But at least now we kind of have an idea that our parabola is going to be somewhere shifted to the right. So if the vertex is the middle point, then the point above that's just going to be 1 less than the vertex. Let's double check that. If I were to plug in 1, 1 minus 2 is -1, and -1 squared is an output of 1. So that works. On the other side, 1 more than the vertex would be 3. Let's check that really quick. 3 minus 2 is 1, and 1 squared is also an output of 1. 1 less than that would be 0, because 0 minus 2 would be -2, and -2 squared would give us an output of 4, and 1 more than 3 would be 4. 4 minus 2 is 2 squared, which is also 4. So you can kind of tell in a table that you're always going to have your vertex as your middle point, and then points above it are less than the vertex, and points below it are greater. Okay, so step 1 is done. We have found our set of inputs. Now we can actually go in and start applying the different transformations. So the first transformation will be the stretch here. So we're just going to multiply each of our outputs by that factor of 2. 9 times 2 would give us an output of 18, 4 times 2, 8, 1 times 2, 2. So now that we're done with our stretch, we're going to add 2 to each of those outputs. 18 plus 2 is 20, 8 plus 2 is 10. So these are the final outputs for our function. But there's a lot going on in this table. So when it comes to actually graphing it, what are we expected to look at? Well, you have to remember that the columns in the middle were used to help us get to the final function in the final parabola. So simplify it to your input, your first input, and your final output. So the first point that we're going to plot in our function is going to be at negative 120. And that's actually where this point ended up after all of our transformations. So take a moment to find the rest of the coordinates and plot your final points of your transformed graph. So here is the final graph. After everything that we've done, we can say that this graph was stretched by a factor of 2. It was shifted up 2 units, and it was shifted to the right 2 units from the original parent function. Let's take a look at another example. Again, looking ahead, I already know that this graph is going to have a shrink by a factor of 1/2. It's going to be shifted to the left 2 units and down 2 units. So again, starting off here, we just want to direct our attention to our inputs. Where has that vertex point shifted to? So we're trying to create an output of 0. What plus 2 gives us an output of 0? That would be the output of negative 2. So when I plug in negative 2 to my function, negative 2 plus 2 is 0. 0 squared gives us that unique point. So already I can predict that my graph is going to shift to the left. That's not where my vertex is going to end up because we have additional transformations to complete. From here, we can fill in the rest of the points in our table. Negative 3, negative 4, and negative 5 will produce outputs of 1, 4, and 9. You can check that math if you want to. Negative 1, 0, and 1 will also produce outputs of 1, 4, and 9. Now we can apply our shrink. So half of 9 is 4.5 or 4.5. Half of 4 is 2, 1/2, 0. Last but certainly not least, let's go ahead and apply our vertical shift. So we're taking our new inputs and subtracting 2. 4.5 minus 2 gives us 2.5, 0, negative 1.5, negative. Now that we've applied our final transformation, let's go in and identify our ordered pairs. For the new input of negative 5, our output will be 2.5, which appears to be the point right here. So there is our newly transformed point. Go ahead and finish off your graph now. And here we have our final graph. So again, this graph underwent a vertical shrink by a factor of 1/2. It was shifted down 2 units, and of course, as we saw at the beginning, also horizontally shifted to the left. To quickly recap, we studied all of the different transformations in this video. Multiplying a graph by a value will either stretch, shrink, or reflect it, depending on that value of A. Whatever's inside of the parentheses will shift it left or right, and it's all dependent on what value of X will make that 0. And then finally, whatever you're adding on to the end will either shift your graph up or down that number of units. When it comes to actually graphing these transformations, work your way inside out. First step, find your inputs. Specifically, where is your vertex going to be located? Put that point in the middle and then find your points above and below. Step 2, apply any stretches, shrinks, or reflections. And step 3, find your final outputs after applying any vertical shifts. That's it for today's lesson. I will see you next time.